Okay, this notes page is for limiting values, end behavior, and asymptotes, and I might split it up into a couple of videos. So we'll start with end behavior. And I have to give you a few definitions before we go into the graphing part. Unit 1 in Math 171 as it currently is constructed is mostly just graphs, but I have to give you some definitions so we can talk about what we're seeing. So this is the general form of a polynomial function, and don't let the letters scare you. This a sub n is just a number, and then x is a variable. It'll stay x to the nth power. That's a number, and it might be 5, 6, 7, 8, 2, 3. So a x to the n plus another number, a sub n minus 1. That's just another number, x to the n minus 1, where it's 1 smaller than that. So this is a polynomial where it's written in descending order. Okay, the numbers a sub o, a sub 1, a sub 2, all the way to a sub n. Like I said, these are all the coefficients. They're numbers, coefficients of the polynomial. They're just numbers. This a sub o, the one at the end, the number at the end doesn't have an x with it, so it's called the constant. It doesn't have a variable with it, so it's called the constant. And then this number here, a sub n, it's the coefficient of the highest power. See how that n is higher than n minus 1? So this is a really important term, and this a sub n is known as the leading coefficient. It's the number in front of the variable that has the highest power, the leading coefficient. And like I said, a sub n, x to the n is the variable that has the highest power, so that's called the leading term. Okay, so let's look at an example. Let's say we have this function p of x is equal to 3x to the 5th plus 6x to the 4th minus 2x cubed plus x squared plus 7x minus 6. Again, this is the leading coefficient, 3. This is the leading term, 3x to the 5th. This is the degree of the polynomial. The degree of the polynomial is, you don't add up the exponent, it's the highest degree. So that is a degree 5 polynomial. The coefficients are 3 and 6 and negative 2 and understood 1 and 7 and negative 6. And this negative 6 is the constant term. And the cool thing is, for a lot of our end behavior discussion, all you really need to look at is the leading term. So the leading term has the greatest influence on the end behavior. Of a polynomial function. So even though we're just mainly looking at graphs, we're going to go ahead and talk about this now. So if a polynomial has an odd degree where the leading coefficient is positive, like this, if we had f of x equals a positive leading coefficient, an odd degree, and then don't really care about anything after, okay, then that leading term is going to determine the end behavior. Okay, and so here's what the end behavior is going to look like. We'll just sketch it. Here's the y-axis, here's the x-axis. So an odd degree with a positive leading coefficient is going to be an increasing function. From our last lesson, we know what increasing means. And look at the end behavior. Okay, so the end behavior, this is the quadrant 1, and these are your x values. So x is this way, it's positive, and y is this way, that's positive. And this here is going when x is negative, y is negative. So we'll write that as x approaches positive infinity, y approaches positive infinity. So the plus there. And as x goes to the left, or negative infinity, y approaches negative infinity. Now in words, we call that down-up behavior, because it starts out with the arrow down and ends up with the up, but this is how you describe it. Alright. right? If you have an odd degree and a sub n is less than 0, that means it's negative. That would be like f of x equals negative 2x to the 5th plus, and we don't really care about anything else because the leading term has the greatest influence on the end behavior. So if I sketch that, what's going to happen is this negative 2 is going to flip what was up here. It's still an odd degree, so and maybe it has a few extra humps in it, but we don't really know what the middle part looks like. We're just looking at the end behavior. So this quadrant is negative positive, and this quadrant is a positive negative. But the way we describe the end behavior is as x goes to the right, as x goes toward a positive infinity, y is going down to negative infinity. But as x goes to the left, negative infinity, y is going to positive infinity. So that's the language we use. Or if we just want to use words, we can say this has up-down behavior. Okay, so if you have an odd degree, both of these are going in opposite directions. That's nice. Odd degree, opposite directions. And if this is a positive a, you know, we've learned about increasing functions. So a positive leading coefficient gives you an increasing function, and a negative leading coefficient gives you a decreasing function. So that makes sense. Alright, so let's say you have an even degree. That would be something like if f of x equals an even degree where a sub n is positive. So let's say I have a positive 5x to the 4th plus, and I don't care what's next, because the leading term is all I care about. Then what's going to happen is you're going to have something called up-up behavior, something like that. So again, this is plus plus, and this is negative plus. So when we write it this way, as x goes to the right, or positive infinity, y is going to go up, or positive infinity. And as x goes to the left, y is going to go up as well. So we call this up-up behavior. And the even degree, if the leading coefficient is negative, that would be something like, let's say we have a negative 2x to the 4, or let's do 6, plus 5x to the 5th. We don't care what's next. It's just, this is the highest power. The highest power has an even degree, and it's a negative. It's going to do what happened up here. That negative is going to flip this upside down. Now we might have a couple of more bounces because the degree is higher, but what we're caring about is the end behavior. So again, this is positive negative, and this is negative negative. As x goes negative, y is negative. We'll write it this way: as x goes to positive infinity, as x goes to the right, the y coordinates are going to be heading towards negative infinity. And as x goes to the left, negative infinity, the y coordinates are also going to be going towards negative infinity. So that's what we call down-down behavior. And you can see that if you have an even degree, the end behavior is the same. It's just the negative is that what flips it upside down. So again, this unit, we really look at the graph more, and you have to describe the end behavior, but can't get away with not really looking at the polynomials. So here's just 4 examples. You can stop the video if you want, practice. Describe the end behavior of the following polynomials. So these are all in descending order. See the x to the 4th, x to the 3rd, x to the 1, and the 5. That means I don't care about anything but the leading term. So this leading term is a negative leading coefficient but an even degree. So this is going to be down-down behavior. But we want to practice writing this out. So as x goes to the right, or as x goes to the left. Okay. Y goes to down, and y goes down. So B, it's tricky. you have 4x to the fourth, and just because it's in the first location doesn't mean it's the leading term. You have to look for the highest power. So this negative 5x to the fifth is actually the leading term. And it has an odd degree and it's a negative, so it's a decreasing function. It's going to look like this, up, down. And what that means is, as x goes to the right, positive infinity, y is going to go towards negative infinity, and as x goes to the left, y is going to go up. So sometimes it's helpful to draw the picture. Alright, C, the leading term is 3x cubed. So that looks like this, down, up. So that means as x goes to the right, y goes up towards a positive infinity. As x goes to the left, x goes to negative infinity, y goes down to negative infinity. And then the fourth one, you have 4x cubed, you have 5x to the sixth, 6x, x squared minus 31, that's your leading term, positive 5x to the sixth. So this one is going to be up, up. So that means as x goes to positive infinity, y goes to positive infinity, goes up. As x goes to negative infinity, y also goes up. Okay. Alright, let's continue talking about end behavior and continue talking with this notation here. End behavior of an exponential function, it's not like a polynomial because you have some leveling off going on here. So that's going to make things a little bit harder for students. And I have learned from giving a quiz on this a couple of semesters, people aren't understanding this that well. So I'm going to try to take my time here. Alright, end behavior of an exponential function. The end behavior of an exponential function, f of x equals b to the x, that's what an exponential function looks like. So we've moved away from polynomial. You got to forget all that ax to the n stuff. This isn't a polynomial function. This is an exponential function. It has a base. So like it would be something like f of x equals 2 to the x, or f of x equals 1/3 to the x. Something with a number here in that spot and a variable in the exponent. Okay? And the end behavior is determined by what the number is here or here. Okay? So, first example, if this number here is between 0 and 1, that means if it's a fraction, that's like this, then what's going to happen is you're going to have decay. Not growth, but decay. That means as x gets bigger and bigger and bigger and bigger, and if you watched my Desmos video, I think I talk about this, then y is going to get smaller and smaller and smaller and smaller, but it's not going down, down, down. It seems to be leveling off somewhere, right? And so exponential functions, all of them have some sort of horizontal asymptote, which I'm skipping ahead, but we have to talk about that now. You can kind of see that this exponential, and you have to know this about exponential, it's never going to hit a certain, it's got like a boundary called a horizontal asymptote. It's going to approach y equals 0. Y is going to get so tiny and tiny, 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 it's going to look like it's going to equal 0, but it never really will quite get to 0 theoretically. Okay, so that's going to change the way we write our end behavior. This side makes perfect sense. It's just like what we just learned. It's when x is negative, y is going up to positive infinity. So as x goes to negative infinity, y, that's another way to write y, f of x, goes to positive infinity. That's just like polynomials, but over here it's a little different. An exponential is going to have this leveling off property. Okay, so what this means is that as x goes to the right or goes to positive infinity, as x gets really, 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 really large, like you can put it in the calculator and see. As, let's see, if I have 1/3 and I raise it to the, and let's make it 1,000th power, as x, well, little crazy there. 1,000. How about that? That's a really large number. So as x is 1,000, turn things back on. Here we go. When I hit enter, you're going to get a really small number. Oh, it doesn't even want to tell you the number. It's just going to say 0, but it's really not 0. What it is, let's see what 3 to the 1,000 is. It's got an overflow error. So I went too crazy. Let's make it 100. How about that? Okay. 5.15 E47, that means 5.15 times 10 to the 47th power. It's so small. So if I put 1 over that number, it's 1.94 times 10 to the negative 48 power. It's so small, it's like 0.00047 zeros 19. Theoretically not 0. So it's never ever going to actually touch this horizontal asymptote. So, trying to explain it so you understand what this notation means. As x goes to infinity, that means as x goes to the right, that means as x gets really big, y is going to, see that arrow doesn't say equals, it's going to approach 0. So whatever your horizontal asymptote is, that's what it's going to approach. Alright, same thing over here. This is an exponential growth. This is decay. This is growth. As if the number right here is greater than 1 like this, f of x equals 2 to the x, for example, that means as x gets really large, when x is like 1, 2 to the 1 is 2. When x is 2, that's 4. When x is 3, that's 8. When x is 4, that's 16. When x is 5, that's 32. When x is 6, that's 64. When x is 7, that's 128. So as x gets larger and larger and larger, that's not, hopefully, I don't mean to insult anybody, but that's like what we just learned. That's just as x gets really, right here, as x gets really large, y gets really large. No big deal there. But notice what happens as we make x go really small. There seems to be some sort of leveling off that's happening, and again, it's happening at y equals 0, or f of x equals 0. And same idea, as x gets really small, if I put like 2 to the negative 10 in there, 2 to the negative 10 really means 1 over 2 to the positive 10. A negative exponent flips it. So that's a very small number. Very small number. It's not theoretically 0. It's going to approach 0. So here's what we got here. As x goes to negative infinity, gets really large to the left, negatively, y is going to approach 0. Never quite get it. Alright, so let's do one example for end behavior and exponential functions. And I'm going to shift this function, so I'm going to sketch it. Let's say I have something like that, and I have something like that. Okay, so that's my attempt at showing you what we've got is an exponential function. Do you know whether it's growth or decay? And it would be growth, since as x gets larger, y is going up there. And can you determine the end behavior? Okay, so that's what the question that I've been asking, and people have been missing it. So hopefully this extra example on the note sheet will help you. Alright, so when we're talking about end behavior, that means we're going to write it like this. As x goes to the right. Okay, that means as x goes to positive infinity, f of x, or y, approaches what? Well, as x goes to the right, y, this is a plus, right? It's going up and up. Y is going up to positive infinity. Okay, so the right side of this is as x gets really large, y gets really large. Alright, what's going on as we go look at the left? As x goes to the left, or negative infinity, can you tell me what's going on with y, f of x? Alright, we have to know theoretically, now I drew it so it's a little more obvious, but if it were a Desmos graph, it might look like it touches this line here, but you gotta know, theoretically it does not. Well, what is this line? This is 1, that's 2. So this is the line y equals 2. So as x gets really large, this y value seems to be approaching the number 2. So whatever your horizontal asymptote is, if you can locate that, that's what y is going to approach. Okay, I'm going to split this video up so it's not so long, so I'm going to stop there with end behavior.